Watch this agent navigate a highly complex environment, making rapid, real-time decisions without any human input at all. It moves with precision and apparent strategy. But the agent itself didn't originate these tactics. Under the hood, this system relies on inference time skill augmentation. Whenever it faces a problem, it queries an external database for instructions. A retriever pulls a text document outlining the necessary skill, represented here by the book icon, and injects it alongside the system prompt directly into the agent's context window. The model isn't reasoning from scratch. It is reading a step-by-step tutorial on the fly and executing the commands it finds there. The competence you see belongs to the prompt, not the model. If you clear that context window, the agent loses access to the instructions, and its ability to complete the task immediately collapses. Relying on external text creates an immediate operational constraint. As an agent works through a multi-step task, the history of its actions continually extends the context length. Adding bulky skill documents into that same window at every single step forces the token count to scale aggressively. This also introduces retrieval noise. If the database surfaces a loosely related or contradictory instruction, the agent's trajectory is derailed. Over a prolonged interaction, the sheer volume of text data saturates the model's capacity and drives up computational expense. The logical next step is to ask whether we can take these external skills and bake them directly into the model's internal parameters. That is the exact objective of a new framework called Skill Zero. Skill Zero leverages in-context reinforcement learning. It creates a continuous feedback loop where the agent policy interacts with the environment and updates itself based on the outcomes. By moving the skill library out of the inference phase and strictly into the training phase, the architecture prepares the model to execute tasks entirely zero-shot, without relying on external documents. Running reinforcement learning rollouts requires passing massive skill libraries and long interaction histories to the model repeatedly, which is computationally expensive. To solve this, Skill Zero introduces a mechanism called context rendering. Instead of feeding raw text strings into the model, the system converts the entire textual interaction history and retrieved skills into a single compact RGB image. This equation illustrates the rendering process. The text history and skill data are visually compressed into a dense two-dimensional color grid based on a self-generated compression ratio. A vision encoder then processes this image. The structural information remains intact, but the token footprint shrinks dramatically. During training, the reinforcement learning algorithm evaluates both the agent's success at completing the task and its efficiency in compressing the visual context. This rendering technique reduces the token costs required during the training loop by over a factor of 5. With the computational overhead minimized, the system can now run the complex iterative training stages needed to slowly withdraw the skill prompts. The core challenge of Skill Zero is timing. If you remove the skill prompts too early, the agent fails the task. If you leave them too long, the agent never learns the skill itself. The system navigates this using a specific metric called helpfulness, denoted mathematically as delta K. Every few steps, the framework validates a subtask using two parallel tracks, one where the agent receives the explicit skill prompt, and one where it operates entirely blind. This graph maps the helpfulness metric, forming an inverted U-shape. Initially, it sits near 0. As the model learns, the prompt's utility peaks, outperforming the blind track. Finally, optimization encodes behaviors into the model's weights, narrowing the gap as it succeeds blindly. When the helpfulness metric drops, the algorithm recognizes the model no longer needs the crutch. It linearly decays the skill budget and permanently filters out the prompt. The textual skills act purely as temporary scaffolding, supporting the model while it learns and dissolving entirely once the structure is stable. By gating the withdrawal behind empirical performance data, the system forces the model to fully internalize the procedure before it is allowed to operate autonomously. This training methodology translates to clear advantages at inference time, as shown by benchmark tests on AlphaWorld and SearchQA. This table compares the average success rates among different 3 billion parameter models. The Skill Zero architecture reaches an 87.9% success rate. That outperforms the standard reinforcement learning baseline on the AlphaWorld benchmark by nearly 10 percentage points. It achieves that high score entirely zero-shot. It requires zero text retrieval and zero skill injection at runtime. Looking at efficiency, a traditional retrieval-augmented model like Skill RL consumes 2.21 thousand tokens per step. Skill 0 requires only 0.38 thousand tokens. By dropping the runtime injection and utilizing compressed visual context, the architecture breaks the usual dynamic where higher capability requires higher computational cost. High benchmark scores raise the question of whether the model has actually internalized the knowledge or simply overfit to the test environment. To prove the parameters changed, we analyze validation accuracy over 150 training steps. Crucially, models operate without any skill prompts. The trajectories diverge. Standard RL plateaus early, while SKL0 scales steadily upward, proving the parameters are actively acquiring procedural knowledge. A context-dependent model is rigid. Its intelligence is strictly bounded by the documents it retrieves. A parameter-internalized model grows intrinsically capable. It absorbs the data streams and solidifies the logic into its own internal pathways. Treating external skills as transient tools for training, rather than permanent requirements for inference, provides a scalable blueprint for creating truly self-sufficient AI agents.